T&T Tools Incorporated is a small, family-owned business based out of Holland, Michigan, specializing in the design, manufacturing, and sale of subsurface hand tools. Their most popular products include probes, hooks, and other specialty items. They take pride in producing durable, high-quality tools sourced and produced entirely in the United States. Over the last 2 semesters, T&T Tools tasked our group with the development of a new bending process for the handles on a number of their hook products. This new process was needed in order to produce a more efficient, safe, and environmental-friendly production solution. Currently, the process consists of heating the steel in a forge until red hot, which requires additional time to make each product, along with producing excess heat, noise, and fumes. This process is performed on 2 different bending machines, with the product being readjusted manually by the operator between each bend. Once the metal is properly heated, the first 55-degree bend is made on a rotary bending machine, which you can see here. The rod is then moved to a secondary bending machine to perform the final 2 bends. After bending the hook, the handle is checked and adjusted using manual correction gauges to ensure the critical dimensions have been achieved.
The goal of this project was to design a machine that is capable of bending multiple 1-inch radius bends in a 5/8-inch hexagonal 4140 steel rod to form a hook handle. There were a total of 18 specifications that were listed. However, there were 6 critical specs that determined the course of the entire project. First, every bending method in the process must utilize cold bending to eliminate the use of the furnace. Bending cold will cause springback to occur. Therefore, overbending the rod is needed to account for the degree of springback. Second, the process must be completed on 1 machine. This will ideally save the sponsor room in his shop floor and make for a quicker and more reliable bending process. Third, as was mentioned earlier, the stock that needs to be bent is 5/8-inch hexagonal 4140 steel. Fourth, the gap at the end of the handle, seen in the attached figure on the bottom right, needs to be minimized, which is smaller than 0.05 inches. Fifth, the amount of user interaction needed to be reduced. This would result in a more automated process that would require the operator to only load the part and remove it from the machine once the part was completed. And lastly, the safety needed to be improved. So for example, on the current process, the rod swings toward the operator on the final bend, which needs to be eliminated.
During the design of this machine, several challenges arose. The first was the use of cold forming. When metal such as steel is bent cold, there is a chance of rupture due to a high concentration of stress. A method had to be found that would not cause this rupturing. It was found that applying the force at a point caused a high concentration that would lead to fracture. Therefore, the force had to be distributed over an area. The second challenge was decreasing operator interaction. Optimally, the machine would have little to no user interaction. The part would be loaded, a button would be pressed, and the bends would be completed by the machine. This led to challenges of finding the correct bending order and also bending the part to the required specifications. The next challenge was adjusting for springback. When cold metal is bent, it tends to spring back closer to its original shape. To accommodate for this, the part has to be overbent. The dies had to be adjustable to accommodate for overbending.
To account for the springback involved, an analysis was performed using machines currently available at T&T Tools. In order to collect springback data, raw, cold steel hex stock was bent on each of the machines to determine springback at multiple angles. It was found that samples ruptured at a bend angle of 70 degrees using the DI Acro rotary power bender. T&T's custom-built bending machine, however, was capable of bending raw material to a higher angle without rupture. For larger angles, the measured springback was higher than that of lowered angles. For a final bend angle of 145 degrees, an overbend angle of nearly 155 degrees was required. For a final bend angle of 55 degrees, an overbend of nearly 60 degrees was required. 3 different design concepts were developed to improve the bending process. The first design concept would bend the hook handle around forming dies using 3 cylinders. The pros of this design are that it requires minimal operator input, improves cycle time, is easy to repair, and is safer because the hook end does not move. Conversely, the required stroke length of the cylinders was very long, and properly positioning each of the cylinders would pose a significant challenge. The second concept design also requires 3 cylinders. The first bends are made by moving the entire carriage down onto the forming die. The second and third bends are made by actuating the side cylinders one at a time to form the hook handle into its final shape. The pros and cons of this design are that the process is mostly automated, it requires minimal operator input, it is easily assembled, easily maintained. Cons of this design are that the custom dies are expensive to machine, and it also poses a more difficult challenge to program the PLC. The third concept design performs each bend by pulling it around a bending die with a rack and pinion assembly. This concept only bends around one point and is easily adjustable for springback, but requires the operator to reorient the part after each bend. The second concept design was selected for further development.
During the concept selection phase of this project, a national emergency arose as the spread of COVID-19 was declared a pandemic by the World Health Organization. This provided many challenges for the team, as it did all around the world. With the closing of GVSU, the team was required to complete the design virtually while practicing social distancing. The main concern at this time was the concept selection, since the concept that had presented itself as the best in meeting the specifications used a untested method for bending. With the support of TNT tools, the team was able to get the required testing performed, and a concept could be chosen. From there, the team went through complete design of the concept without meeting in person.
The prototype was first modeled on SOLIDWORKS with key dimensions that would be used within the actual design. The ANSYS simulation used the imported SOLIDWORKS geometry and was set up to solve large deformations with multilinear isotropic hardening properties. The supplier of the rod material conducted a tensile test for the 4140 hexagonal steel rod. The nonlinear region of the stress-strain results was entered into the simulation to account for the nonlinear yielding properties. The SOLIDWORKS model was sent to TNT tools to be manufactured and eventually tested. 3 trial runs were conducted to ensure that the prototype would function the same each time. The prototyping concluded that rupturing would not occur in the material.
Taking a look at one of the bending dies when under an approximate 10,000 pound load applied at this location and 2 points being fixed, this point being in contact with the bending rod, it can be seen that the equivalent stress is well below the 161,000 psi yield stress of heat-treated 4140 steel. The probed total deformation shows small values even at the maximum point, and the factor of safety can be seen as very high, proving in fact that this is a safe design. When looking at the fatigue tool, the only point that can be seen below infinite cycles is where the maximum stress was experienced. The consistent load that this die would be under would be much less than 10,000 pounds, which would yield infinite cycles at this position. Originally, a 3x3 by quarter inch square tube was used for the carriage, but displayed high stress at critical places on the frame. Therefore, a 4x4 by half inch square tube was chosen for the carriage, and this was to be able to withstand a 10,000 pound conservative load being applied from the side cylinder. As seen in the display, there are the 5 fixed supports, as well as a force that is given off from the hydraulic cylinder at the angled clevis mount. Taking a look at the equivalent stress on the frame, from the probes, it can be seen that the majority of these stresses are below the 46,000 psi yield stress of ASTM A500 steel square tubing grade B, which is what this carriage is made from. These 2 high areas of stress, as you can see probed, is where the maximum occurs, but these are due to stress risers, which is from importing the assembly into ANSYS, and it can be seen that these mates are causing these high stress risers. Taking a look at the total deformation probes, it can be seen that even at the maximum value and the maximum position, none of these are values they need to be worried about. High factor of safety was seen throughout the entire portion of the carriage when this load was applied. Now, taking a look at the fatigue tool, it can be seen that infinite life is not experienced at this position. This is due to the fact that this bearing load is a approximate 10,000 pound load, which is a very conservative force, which is it's only going to be seen at minimal periods of time, where a more consistent load would be somewhere around 5,000 pounds. Now, taking a look at the fatigue tool, you can see while probing that infinite life is experienced, besides at those stress risers that were talked about earlier.
Once the force required to make each bend was found and verified, a hydraulic system was designed in order to supply said force. Since pneumatic systems are generally for lower force applications, a hydraulic system was implemented. This system was designed for 3 gallons per minute at 1500 psi with 3 cylinders in a series circuit. In order to achieve control over extension and retraction of each cylinder, tandem center directional control valves were used. These valves are controlled by PLC via 2 solenoids each. When no solenoids are activated, the spools are centered, allowing flow through each back to the reservoir. However, when a solenoid is activated on the valve, forward or reverse flow into the corresponding cylinder will be initiated. It is important to note that this system only allows for 1 solenoid to be active at a time. However, the system does allow for different lengths of extension simultaneously. Once the requirements of the hydraulic system were known, the electrical system was developed to meet them. The electrical system was designed around an Allen Bradley Micro 820 PLC. The PLC is powered by a 24-volt DC supply. It takes push-button input for operation and uses Hall effect sensors at the cylinder rods for the sense input of rod extension and retraction positions. The PLC also controls directional control valve solenoids, which helps allow for minimal operator interaction in the bending process. A 3 horsepower AC motor is used to power the hydraulic system. This motor is turned on and off by the PLC via the motor contactor and can be manually shut down by a Category 0 e-stop in case of emergency. Finally, in order to facilitate increased longevity in the motor's life, a circuit breaker and overload protection were designed in line with the motor.
This new design and process for the bending of hook handles is a significant improvement over the current process. The new process removes the need for heating the metal and requires only one machine without requiring the operator to reorient the part between bends. As a result, it provides a safer, more environmentally friendly, and most importantly, more efficient alternative to the current process.